there, that video. What we are starting with, energy storage and regeneration. So what is the concept of regeneration? I told you that whenever the vehicle goes down, at that time, what happens is the battery gets charged by the vehicle. So that is called as regenerative braking, or that is called as regeneration. So energy storage and regeneration means these are the two main ways the battery is getting charged. And energy storage, whenever I am saying, it is not only about battery. There are few other things which can be used as a energy storing devices. So here is the brief outline of your syllabus. If you see the syllabus, you'll be finding the same things. So initially there is the battery, and it is called as a electrochemical devices. So that's why electrochemistry, knowing electrochemistry is also kind of important for you. So electrochemical batteries and its types. So these types I will not be asking in the exam. So there will be very less theoretical questions from it that explain battery. It will not be asked like that. But at least we should know what are the different types of batteries. We all know that we are mainly using lithium-ion battery now. But what were the previous types of batteries which was there in the market? That also we are going to see. So electrochemical reaction, thermodynamic voltage, specific energy. So there are a lot of short questions I can prepare from this module. And these first 2-3 lectures, it will be a little more difficult because it is not pure electronics. It is somewhat like electrochemistry, more chemistry related. I think all the equations you have already seen in your 10th and 12th standard. So a little bit of that we are going to see today. Now there are very two important equations, which one is called as a specific energy and another is called as a specific power. These two energies definition is very important. What is meant by specific energy? What is meant by specific power? What is meant by energy efficiency? So whenever there is efficiency, I remember efficiency is always meaning that output upon input. Okay, so whenever I am saying energy efficiency means how much input you are giving to the system. Let it be in terms of battery energy, or let it be in terms of fuel or something, and how much output you are getting. So output you are getting, it can be calculated or it can be estimated by the power that the vehicle is developing. So how much power the vehicle is developing, it is in the mechanical domain. So we have to calculate mechanical power divided by electrical energy or maybe fuel energy. So whenever we are inputting fuel, let's say diesel we are inputting. So in 1 liter of diesel, how much of energy is concentrated, that we have to calculate. So input and output quantities are different. Output can be mechanical quantity, and input can be either from fuel or from battery. It can be electrical if it is battery. If it is fuel, it can be a electrochemical kind of energy. So all these things we have to learn. It is not directly there in this slide or anywhere. I'm just giving you a glimpse what we are up against. So what is energy efficiency? We are going to see different battery technologies for EV and HEV. HEV means hybrid electric vehicle. So hybrid electric vehicle means it is petrol or diesel and battery together. And whenever I'm saying EV, it is only battery. Battery management system, BMS, very important topic. Battery management system is totally guided by embedded systems. So if you are good in embedded systems and if you want to join EV or EHV field, then you can blindly go into the field of battery management system. Huge amount of work is going on and many more things to do. Okay, so this is all about batteries. That is our first topic. Next, there is coming some 3 new topics which you have not heard much. So one is called as ultra capacitor. So very big kind of capacitor which is charged once, and then you can use that charged capacitor in substitution of a battery. That is actually called as ultra capacitor. We are going to see in the next days. So features of ultra capacitor, basic operating principle. Performance of ultra capacitor. Performance means how fast or how soon does it discharge. So ultra capacitor means it is going to give you some very fast discharging current and all, and that is actually running the EV. So how to estimate the performance of ultra capacitor, that we are going to find. Different types of ultra capacitor technologies that is there. So all these things we can find in the chapter number 13 of the book of Ehsani. So all these things is all the topics are not going sequentially in the textbook. Textbook is already uploaded in your Google Classroom in the very first day. So in that module number 13 and 14, you will be finding all the things which is there module 3 for our syllabus. Then there is coming ultra high speed flywheel. So what is meant by flywheel? Those who are doing this vehicular technology internship, they have seen the flywheel. So flywheel is one device which is a very big mechanical chaka kind of a thing. It's a very big mechanical wheel that is actually connected with the engine. Okay, so whenever the engine rotates, flywheel also rotates with a very high inertia. So suddenly, if you stop the engine actually should not stop delivering power. Suddenly, for some reason, if the engine takes a pause, but the flywheel keeps on rotating. So whenever the engine stops, then the flywheel keeps on rotating the engine, so because of its inertia, and after a certain time again engine is started. So between this pause, whenever the engine is paused, flywheel keeps on generating the power which keeps the engine on. So what are the different kind of flywheels? We will see what is the operating principle, what is the power capacity, different technologies, and all those things we are going to see. Finally is coming fundamental of regenerative braking. What is meant by that? So energy consumption in braking, brake power, brake energy, brake power in the front, brake power in the rear wheel, brake system for EV, HEV. So there is a video for brake system. I was telling from the very first lecture, I will show it, but I have not shown that to you. But whenever we are doing fundamental of regenerative braking, I will show you first that video, that what is disc brake, what is drum brake, how they are functioning at the wheel of ICEV, and then I will go for explaining what is in a regenerative braking system. So there is a case study. Case study is ultra speed flywheel. It is mentioned in your syllabus, but whenever I'm doing the third topic of ultra high speed flywheel, there we are going to cover this case study of ultra speed flywheel. So we are starting with the first topic. We are in the module 3. So in this 3 lectures this week, before your IA starts, we are planning to finish the first topic, that is the batteries and its types. Next, we are going to see what is meant by battery. So this slide and all the slides, wherever definitions are there, very important. So please prepare them properly. So it is said that energy storages are defined as the devices that store energy. It is very important. Delivers energy outside, which is called as a discharge, and accepts energy from outside. So those who have pen and paper, you can remember or you can write down that there are 3 ways a battery inside the vehicle can be charged. One way is so if it is a EHV, that is, I'm assuming that it's a hybrid vehicle. So whenever it's a hybrid vehicle, first you can charge the battery directly. That means from the outside, if there is a charging station, from there you take a plug and you connect to the battery of the your EHV. Okay, and that way you can charge the battery. That is the first way and simplest way. Second way is it is a EHV. That means it's a hybrid vehicle. So hybrid vehicle means there are 2 powertrains. One powertrain is taking the power from the fuel. Suppose if it's a petrol and battery hybrid kind of a thing. So petrol to the final wheel, that is one powertrain, and battery to the output wheel, that can be another powertrain. So either the petrol will run the battery, petrol will run the wheel, or the battery will run the wheel. So these are the 2 power trains we can talk. Sometimes what happens is whenever we are on the highway or something, what happens is whatever power is generated by the main source is petrol. Okay, so whatever power is generated by the main source, 80% of that power is given to the wheel, and 20% of the power is fed back, which charges the battery. So this is the second type of charging, that is one source is charging the other source. So what I'm telling you is, I'm telling you that the battery inside the EHV, that is hybrid vehicle, can be charged in 2 ways. Now, mainly 3 ways actually. So first way is direct charging. Second way is the first source, petrol, it is running the vehicle, and while the vehicle is being run, there is a rotation, motion, and all those things. And there is another path, which is feedback kind of path, which is actually giving the energy from the petrol source to the battery. So one source is charging the other. So this is the second way of charging the battery. What is the third source? Third source is regenerative action. That means whenever the vehicle is going downward, at that time the output motor, it acts as a input generator. So at that time, whenever the vehicle is going down, at that time the output motor, which is driving the wheels, that actually acts as a generator, and power flows back from the output to the input side, and the battery gets charged. So these are the 3 ways. If you are having pen and paper, you can please write down that this question, that what are the 3 ways the battery can be charged. Number 1 is direct charging of the battery in case of EHV. Second way is regenerative action. That means whenever the vehicle is going downward, at that time the output motor, it acts as a input generator. So at that time the output motor, which is driving the wheels, that actually acts as a generator, and power flows back from the output to the input side, and the battery gets charged. So these are the 3 ways if you are having pen and paper, you can please write down that this question, that what are the 3 ways the battery can be charged. Number 1 is direct charging of the battery Second case is the primary source is charging the secondary source. Secondary source is the battery. Primary source can be petrol or diesel. And third thing, which is very important, that is called as regenerative braking. So whenever the vehicle is going down, at that time, the output motor acts as an input generator, and that feeds the power back, and that is actually charging the battery. So several types of energy storage have been proposed for EV and HEV. This energy storage mainly include chemical batteries, ultracapacitor or supercapacitor. So ultracapacitor can also be called as a supercapacitor. There is ultra high speed flywheel and fuel cells. Okay, so fuel cell we are not going to study in this course. So fuel cell, I can upload some lecture videos, or I can upload some videos from YouTube. You will come to know what is meant by fuel cell. Those who are selected in Daimler last year, Daimler is now known as Bharat-Benz, that is actually preparing truck. And many students have been selected last 3-4 years. At least I can tell you 25 to 30 students from EC department have been selected in the Daimler truck Bharat-Benz. And Bharat-Benz has established their research center in Bangalore. And Daimler truck, previously it was called as a Daimler truck, now it is called as Mercedes-Benz truck division, or it is known as Bharat-Benz. They are mainly working toward development of truck, that is very heavy duty powertrain vehicles, by using fuel cell. So it will be totally fuel cell driven, or it is hybrid fuel cell driven. That means petrol and fuel cell, that I don't know at present, but that truck at some point of their operation, they are using fuel cell as the main power source. And what is a fuel cell? Fuel cell is taking hydrogen as the input, and they generate electric power, and output or byproduct from that fuel cell is nothing but water. Okay, so that is very clean source of energy, green source of energy. And Reliance, as I told in the class, Reliance is heavily investing in fuel cell based trucks and all those things. And Reliance has established many hydrogen generating stations or hydrogen distribution stations. So instead of petrol, you are going to have some petrol bank, we call it, or petrol pump, we call it. We'll be having hydrogen pumps, or we'll be having hydrogen bunks. So there are many such things have been established by Reliance. So hydrogen is the future. So that is another storage device. Those, it is not there in your syllabus, fuel cell, but you can go through it. So whenever the Bharat-Benz comes or Daimler comes, in those interviews, fuel cell based vehicle may be asked. So you have to say that yes, you know about fuel cell based vehicle, and you can prepare for that. So those who want, you can search on YouTube, some videos I will also upload. There are many requirements for energy storage applied in automotive applications, such as, now this is the paragraph where the definitions you have to prepare. First one is what is meant by specific energy. Second is specific power. Third is efficiency. Efficiency is output power by input power. Fourth one is maintenance and requirement, management of energy, and SOC. SOC is state of charge. How to calculate state of charge in a battery at any point of time. That I will show you a video today, and you have to understand that video. There is a numerical, I have just cropped that video, you will see today. Environmental adaptation and friendliness, that is how the source, energy source or power source, it is environmental friendly. So IC engine based vehicle is not environmental friendly, but fuel cell is a very environmental friendly device. Okay, so environmental adaptation is that. And safety. So whichever thing is more safe, so battery is kind of a safe, but if there is an accident, battery might explode. And a lot of EVs we are finding nowadays, they are exploding. So battery is no more a safe thing for EV. Okay, a fuel cell. So fuel cell is totally safe, because fuel cell will never burst, because fuel cell is mainly a thing which is made of a membrane. Okay, so there is no things inside the fuel cell which might burst. So fuel cell is very safe and environmental friendly that way. So these are the definitions, very important: specific energy, specific power, efficiency, management of energy, SOC, like this. So for application on EV, specific energy is first consideration. So you can write down these two definitions are very important for exam. What is meant by specific energy and what is meant by specific power? And I ask this as differences, and I ask this as questions. So 5 to 6 mark question you can expect on this. What is meant by specific energy? So for EV application, specific energy is the first consideration. For HEV application, specific power is the first consideration. You can write it down in your notebook. For EV, what we want is sources with high specific energy. For HEV, that is hybrid electrical vehicle, we need a vehicle, or we need sources with high specific power. So it is written here. For EV, specific energy is a first consideration since it limits the vehicle range. So for EV, first thing we require is the vehicle should be having higher range. Higher range means for one battery charge, it should go for longer distance. And for that, specific energy high means it will be giving you higher range. I will tell you all the definitions later. On the other hand, for HEV's application, specific energy becomes less important, and specific power is the first consideration because all the energy is from the energy source and engine or fuel cell. So for HEV, specific power should be high. For EV, specific energy should be high. Sufficient power is needed to ensure vehicle performance, particularly during acceleration, hill climbing, regenerative braking, etc. So whenever I am saying specific energy, now again I am repeating the same thing many a times. Specific energy means what can be the longest range of the vehicle, irrespective of its performance. What is meant by performance? Performance is how is it climbing the hill, how good it is in climbing the hill. Okay, how fast you can accelerate from 0 to 100. So there is something called as acceleration time, TA. You can write this definition. What is meant by acceleration time? Acceleration time is the time of the vehicle to reach from 0 to 100 kilometer per hour as fast as possible. So if some vehicle is coming from 0 velocity to 100 kilometer per velocity in 7 seconds, then we can say that acceleration time of the vehicle is 7 seconds. Smaller the acceleration time, better the vehicle. So for HEV, that is hybrid electric vehicle, we want the acceleration time should be shortest. In that case, we are going to see some power source which will be having high specific power. Okay, but for electrical vehicle, we want the sources, power sources, to have high specific energy, because higher the specific energy, longer the range it will be able to go. So here it is written, sorry, in purple color, that is sufficient power is needed in case of HV, particularly during acceleration, hill climbing, regenerative braking. These are all characteristics for high specific power. Of course, other requirements should be fully considered in the vehicle drivetrain development. So there is a question directly, definition of specific energy, definition of specific power, where specific energy is required more in case of HEV, where a specific energy is required more, that is EV, where specific power required is more, it is HEV. Those things you have to remember. This is the electrochemical batteries. Definitely, I'm not going to explain this. Only what you have to know is this is an electrochemical device. Things required is we need a two electrodes. One is called as a cathode, and another is called as an anode. So negative electrode, this is a positive electrode, and there should happen ion migration into it, and there should be an electrolyte. That electrolyte is very important for moving of the ion from one place to the other. So whenever from this electrolyte only the ions are going from one side to the another side. So this N is the negative side, P is the positive side. Whenever I'm saying N, so electrons are moving from N to P, like that. Current is moving from P to N, likewise. And electrolyte is something through which the reaction is taking place. So there should be a certain amount of water inside this. So this electrolyte is kind of a liquid kind of a thing. So battery is an electromechanical device that electrical energy into potential chemical energy during charging and converts the chemical energy into electrical energy during discharge. So where is the EV connected? So whenever I'm saying EV, EV is nothing but a motor. The motor is connected between this positive and negative. Okay, so between the electrodes, the motor is connected. So from this N, actually, all the electron starts, they flow through the motor, and they comes with the to the P. Okay, and current actually is flowing to the opposite side of the electron flow. So current will be flowing from P to N. This is how the battery is designed. So battery is composed of several cells stacked together. So whenever I'm saying it's a 12-volt battery, in that case, okay, somebody has raised a hand. Yes, Manoj Malonkar. Doubt? Somebody has raised a hand. If you have any doubt, you can ask, or I can go forward. Fine. So battery composed of several cells. So I'm saying it's a vehicle which is having a battery. If I'm saying it's a battery having 12 volt. Actually, it's not a 12-volt battery. It's 6 batteries of 2 volt each. They are stacked in series. Okay, so there is no battery direct, a 12-volt battery connected in a vehicle. There are 6 batteries of 2 volt each. They are stacked or they are connected in series. So a battery is composed of several cells stacked together. So two 6-volt batteries are stacked together. Cell is an independent and complete unit that possesses all the electrochemical properties. Battery cell consists of 3 primary elements. There are 2 electrodes, positive and negative, and electrolytes. The electrodes are immersed into the electrolyte. So that's why we have to keep on continuously. So previous age battery, they wanted water. We need to, it was required for them to put continuous water into the battery. That would actually make the electrolytes liquidified, and that will help the ion exchange. But present day batteries, so we are going to see in the next lecture some other day, that present day batteries, they don't require water to be put into it. Okay, so there is change in the battery technology, and I'll tell you, whenever I'm saying EV is all about battery, because after every 4 or 5 years you have to change the battery, and that battery comes quite costly. Okay, there is no recurring cost directly at the starting for the vehicle usage, but battery cost is very high, and we have to keep on changing the battery every 3 or 4 years. So there is a certain time duration. That is one caution. Another caution is you can rough use the IC engine based vehicle. Okay, कुछ भी करो, engine is getting little pressurized, but engine is not going to burst. Engine lifetime is not going to reduce very badly. Okay, little bit rough use of IC engine based vehicle is okay, but EV is very sensitive. Okay, whatever bad things you are doing, it is going to reduce the lifetime of your battery very drastically. So battery is like the heart. Okay, I have told you in the class that if I'm eating junk food together, if somebody is smoking, somebody is drinking, okay, and they say, okay, kuch nahi hota hai, chalta hai. Okay, so those things are not going to kill you. Smoking, eating oily food, drinking, all those things, they are not going to kill you instantly, but definitely they are going to reduce the efficiency of your heart. So a person, if he was living for 90 years, definitely his heart will get bad condition, so it will get damaged slowly, and maybe instead of 90 years, that person will live for 80 years. So this is the difference. So whenever I am using EV, I should be extra cautious about the life of the battery. Okay, so whenever they are saying you be in this range, you take these precautions, you do regular maintenance, that is very much necessary to be done in case of EV. That much care is not required in case of IC engine based vehicle, but EV is little sensitive. And whenever I'm saying EV, it is mainly the battery. Very important slide, you can mark this. This is slide number 5 in this PPT. What is meant by ampere hour? So you can see this top diagram. This is a 44 ampere hour battery. So 44 ampere hour battery means y-axis it is cell voltage. So this diagram also I can ask, or the below diagram also I can ask. There are 3 different ranges which are meant for you to understand. One is called as a normal range. So top diagram is for normal range. You can see that the battery voltage is starting from this point. It is not written here, so there is some voltage. Let's say it is 2 volt. Okay, so y-axis is cell voltage. I think it should be mentioned 2 volt. But this is how the discharging happens. So this is how the current actually is reducing. So at 2.2 ampere, you are going to find that the current, suddenly the voltage is dropping. You can find here. So this is 2.2. This is 2 volt at the top, or this can be 1.7 volts, something like that. All these things are not written, but you are finding that for 20 hours continuously you are getting a current of 2.2 ampere. This is very significant. So even if the battery voltage is 2 volt, or even if it is 1.7 volt, these two things are not marked, but always the battery will be supplying you 2.2 ampere. And how the ampere hour is calculated, it is written here. It's a 44 ampere hour battery. Spec means specification. So cutoff voltage of typical battery, suddenly you are finding as soon as it is coming to 1.7, suddenly the voltage is dropping almost to 0. And this is the discharging time. So from 0 to 20 hours. So for 20-hour time, you are going to get 2.2 ampere. So how to calculate ampere hour of the battery? So ampere hour is actually a power rating of the battery. It is 2.2 into 20. That is giving actually you 44 ampere hour. Somebody says that I'm going to take, you can say 1.1 ampere from the battery. So I'm not going to load the battery more. I'm going to take only 1.1 ampere. So in that case, the discharge time will become 40 hours. Okay. Somebody says I'm going to take 4.4 ampere from the battery. You are loading the vehicle more. You are going to take 4.4 ampere from the battery. In that case, this discharge time will become 10 hours. Okay. So this is how the ampere hour is defined. Whenever I am saying it is 44 ampere hour, means if you are asking for 2.2 ampere from the battery will run perfectly for 20 hours. And after 20 hours, the 2 volt will become 1.7 volt. And below 1.7 volt, you should never make the battery function. Okay, so these two levels are not here. It is 2 and 1.7. And you are finding that after 1.7, suddenly the battery voltage is coming to 0. And this range should never come. Like you should never use your mobile, or you should never allow your mobile to drop to a 2% or 1% charge. Okay, that means you are actually damaging your battery. So as soon as it is closer to 20 or 30%, not even 20, as soon as it is 30% charge remaining in your mobile battery, suddenly you should connect the battery to charging. And you should never take the battery to 100% charging also. That is also bad. So best range is you should charge your battery between 30% to 80%, or best it will be 40 to 60%. When it is 40%, you connect it for charging, and whenever it is 60%, you disconnect it. But in that case, you have to charge or discharge the battery quite a lot of time, quite frequent time. We don't have time for that. So that's why we charge it to 100% and we discharge it to 0%. And this actually reduces the lifetime of the battery. Exactly the same thing is happening here. So battery manufacturers usually specify a battery with colorimetric capacity, which is called as an ampere hour. It is defined as the number of ampere hours gained when discharging from the battery from a fully charged state. So whenever the battery is fully charged, it is 2 volt. Whenever it is fully charged, then I have to decide how much ampere I'm going to take from it. So let us decide I want 2.2 ampere. How long it can give 2.2 ampere? If it's a 44 ampere battery, it can give you 2.2 ampere for 44 divided by 2.2, that is 20 hours time. If you're loading the battery less at 1.1 ampere, if you're taking from the battery, discharge time will be 40 hours. So this is the way, by loading less, you can extend the battery range. That means for longer period of time, you can get that 1.1 ampere from the battery. Below diagram is very important. There are 3 stages. You are finding that first case is that state of charge, SOC, the most important parameter of the battery. And in BMS, embedded system based battery tracking system, always we are tracking battery current, battery voltage, and battery SOC. So if you want to do a mini project or something, you just take a battery and you can define an embedded system. So those who are in such a project, you can take a small battery, or you can take a big battery also. 200, 300 rupees it may charge, a vehicular battery or any battery. And you can find out an embedded system which will be continuously monitoring and displaying what is the battery current, what is the battery voltage, and how much is the battery SOC, that is state of charge, at any point. And how much is the, how to calculate the SOC, I will show you in a slide later. Okay, so state of charge means from 70%, sorry, from 100%, you should fall lowest to 70%. As soon as it falls to 70%, you should keep the battery for charging again. So here you are finding it has fallen to almost 70%, and after 70%, suddenly you are finding that battery voltage is coming to 0. So below there are 3 diagrams. First diagram is that there are 3 graphs. First graph is called as a normal range. So it's a 44 ampere hour battery. You're asking for 2.2 ampere. It is running for 20 hours. This is called as a normal range. Second is, this is the definition you have to find out. It is called as a reserve capacity. Reserve capacity means for some bigger load, you are asking the battery to work for higher amount of current you are asking from the battery. So 25 ampere you are asking from the battery, and it is working only for 1 hour. You will say that it should work for 44 divided by 25, but it is not a linear thing. If you are asking for too much current from the battery, it will not be working for 44 divided by 25. So how much is 44 divided by 25? Let's say it is around 1.8 hours. Okay, but it will not be working for 1.8 hours. As it is working more, as it is exhausting more, you will be finding that within 1 hour the battery will get exhausted. Okay, so with 25 ampere, within 1 hour the battery will get exhausted. It is called as a reserve capacity. And something is called as a cold cranking. What is meant by cold cranking? Suppose your vehicle is there in a very cold country where outside temperature to charge the battery, it takes quite a lot of effort. And whenever you are trying to extract very high energy from the battery in a country where temperature itself is minus 20 degrees centigrade. See, one thing I'll tell you, whenever the outside temperature is very less, at that time, the reaction rate inside the battery and electrolyte and all those things, it goes almost into sleep. So suddenly, if you want to start the battery, you have to give huge amount of energy in a very short period of time. So that is called as a cold cranking. So whenever the battery goes totally cold, sub-zero temperature, suddenly if you're putting the key and you're trying to start the engine, it will not start. So for after few cracking and all, you will find that the vehicle is starting. But during that time, it is asking for almost 170 ampere. Just imagine, in 1 minute. Okay, so this is called as a cold cranking ampere, and most of the pressure and most of the batteries, they crumble. So that's why whenever they are designing vehicle for India or battery for India, where temperature is almost kind of average, 15, 16, 18, 20 degree centigrade. Okay, I'm talking about the average temperature of India. At that time, battery technology is different. But if they are designing battery for Canada, where temperature is always sub-zero and -20, -30 is a normal fact in Canada, their battery design has to be different, because there the battery goes into sleep very easily, because less is the ambient temperature, less is the reaction rate inside the battery, and less will be the energy generation capacity of the battery, and battery will go bad very easily. Same thing happens in case of Arab countries. Their outside temperature is very high. That's why the electrolytes are always in a very highly active situation, and battery is always in a too much of an active state. So there, very easily the vehicle will start, but there is a big chance that the battery will explode in the Arab countries, which is very hot, or in Africa. So there also there should be enough cooling arrangement around the battery. Okay, so India is the best country for this kind of batteries, which is always in the kind of a normal range, or you can say Europe also, the southern part of Europe, or the countries like Italy and Spain and Portugal and all those countries. So they are kind of normal temperature, not too hot, not too cold. So for those kind of countries, we are going to have this kind of characteristic, 2.2 ampere for 20 hour, that kind of range. So this three characteristic is very important. Cold cranking is for very less outside temperature. It is asking for 170 ampere in 1 minute. So huge amount of discharge is being required from the battery, because the battery goes totally into sleep. It is almost dead. You have to start the car when the outside temperature is -30 degrees centigrade. At that time, just to ignite the spark in the battery, just to make it work, the battery has to give 170 ampere in 1 minute. So you're asking for too much current from the battery. So the same battery has different number of ampere hour rating. So depending on the situation, same battery is acting differently. Okay, so normal range 2.2 ampere it will give for 20 hours. For reserve capacity, suddenly you have increased the vehicle. Okay, maybe you're accelerating. There are 5-6 people inside the car, and there may be huge load inside the vehicle. Maybe for 5-10 minutes you have to put too much of load on the vehicle. Right. In that case, the reserve capacity is used. Generally, the capacity becomes smaller with a larger discharge time. So discharge time is more. You can have more discharge time whenever less amount of current is asked from the battery. Battery manufacturers usually specify a normal range for the battery with a number of ampere hours rating on it. So 40 ampere hour battery at C by 20 rate. So this is called a C by 20 rate. That is 44 ampere hour will run for 20 hours. It will be able to supply 2.2 ampere. The same battery with RC, C by C or C by 1, it will be giving you only 25 ampere. Okay, so ampere discharge capacity 20 hours. Same battery has RC 25 ampere for 1 hour and 170 ampere for 1 minute. Okay, see the figure. So both these together can be a question that explain the normal characteristic of the battery. So you have to draw the top diagram. You have to write here 2 volt. You have to write here 1.7 volt, and you have to explain the 3 different characteristics of battery discharge: normal, reserve capacity, and cold cranking. So this can be a 5-mark question. State of charge, here one numerical is there. You have to understand this numerical. The video also is telling you the same numerical. So what is meant by state of charge? So this can be another question. So state of charge at any instant is equal to state of charge in previous instant plus current given by the battery divided by mu n. What is mu n? Mu n is the nominal capacity of the battery in ampere hour. So how much is the nominal battery capacity? It is mentioned in the battery how much current you are asking from the battery, and delta t is the time step. So present state of charge is equal to past state of charge. Suppose battery is fully charged, that means SOC is 100%. So you are going to calculate what is the SOC after maybe 10 minutes. Okay, so SOC initially it is 100%. plus IT, how much current you are expecting from the battery, that you have to mention. What is the nominal rate of the battery discharging capacity, and after how much time you want that. So all this thing, if you fix together, you can find out when the battery will fall to 70% charge. So all these things you can calculate. So this numerical I will explain, or you can see this numerical, it is self-explanatory, you can find out. What is state of the charge? So most important parameter of a battery is the state of charge, which is defined as the ratio of remaining capacity to the full charge capacity. Okay, so it is defined as the ratio of remaining capacity to the full charge capacity. That means whenever the battery is fully charged, 2-volt battery, whenever it is showing 2 volt, at the time SOC is 100%. And whenever it is falling to, suppose, let's say 1.7 volt or 1.6 volt, maybe the charge stored, it is falling to 70%. So 70% SOC means compared to its fully charged state, it has reduced 30% of its charge. And why it has reduced? Because it was supplying to the EV motor load, and that's why discharge has happened, and that's why the state of charge has reduced to 70%. And as soon as it falls to 70%, again you have to start recharging. So with this definition, a fully charged battery has an SOC of 100%, and a fully discharged battery has a SOC of 0%. But we will not wait for it to come to 0%. As soon as for vehicle technology it falls to 70%, we will charge it again. The term fully discharged sometimes causes confusion because of different capacities at different discharge rate. So for fully discharged, the discharge rate is very important, at which rate you are discharging. If the discharge rate is very fast, that is like this previous slide, 170 ampere per minute, in that case fully discharged will be something else. For reserve capacity, fully discharged is something else, and for normal range discharge capacity will be something else. Right. So the charge of SOC is a specific time interval with discharging or charging current IT can be expressed as. So this is the SOC, that is state of charge formula. SOC T is the battery SOC at the time instant T. That means after a certain time. So let's say 1 minute, 2 minute, 1 hour, 2 hour. How much is the current SOC? Okay, this is the after discharge, so maybe 70%. Initial SOC was 100%. SOC T minus 1 is the initial SOC. Mu1 is the nominal capacity. IT is the battery current at time instant T initially. Delta T is the time step. Very important tutorial. It is a 5-mark question. So a 12-volt battery, that means full capacity is 12 volt, has a 500 ampere hour. So this is initial charge range, 500 ampere hour, that is supplying a load of 0.6 ohm. So this is the load. This is the battery. Okay, so battery motor. I'm sorry, not resistance of the battery. This is the resistance of the motor. So this 500 ampere hour battery, it is actually giving current to a 0.6 ohm load. Okay, so load is nothing but the motor, and the battery voltage is actually 12 volt. Find the state of the charge after 3 hours. So I think the numerical is very clear. That is, it's a 500 ampere hour battery. That means that is the nominal capacity of the battery in ampere hour. It is given. So that is nothing but mu1. In previous slide, we have seen a 44 ampere hour battery. That means that is nothing but mu1, and it is actually supplying a load of 0.6 ohm. So first step is finding out how much is the current. So that is VOC, open circuit battery voltage is 12 volt, and it is supplying a load of 0.6. So you have to first find out how much is the discharge current. So this in the second line, it is said IT is equal to 12 divided by 0.6, that is 20 ampere. That means you are asking 20 ampere from the battery for a longer period of time, and time is nothing but 3 hours. So it's a 12 volt battery, it's a 500 ampere hour battery. You are supplying 0.6 ohm, that means you are actually extracting current of 20 ampere for 3 hours. So question is, after 3 hours, how much charge will be remaining inside the battery? That is what we have to calculate. So few things they have mentioned: VOC 12 volt, mu1 500 ampere hour, time delta T is 3 hours. Okay, so 3 hours actually is shown here like 3. Okay, and load current, battery current, that is 12 by 0.6. 12 is voltage, 0.6 is the ohm. So voltage by ohm is ampere, 20 ampere. Battery state of charge, SOC T is equal to SOC T minus 1. So SOC T minus 1 was 100. So previously the battery was fully charged, plus IT. Now IT here is the best thing. You can see that IT, this is discharge current. That's why it is shown as minus 20. This is the only thing you have to understand in this. So IT, whatever IT is here, if it is discharging current, then this instead of 20, it should be written minus 20. And how we have got 20? Battery full voltage divided by load ohm. Okay, So 12 divided by 0.6 is 20. As this is discharge current, we have written minus 20. Divided by battery ampere hour 500 multiplied by 3. 3 is nothing but 3 hours into 100. Into 100 means 100%. Because here, whatever SOCT minus 1 you are finding, this is given in percentage. So this is 100 means 100% plus. Here, this is the discharge current divided by ampere hour multiplied by time. Now, time has to be given in hours. Time has to be given in hours. If I tell you that it is 150 minutes, 150 minutes means 2.5 hours. So everything you have to convert in hour. You have to understand that. So 10 minutes means 10 by 60. That means 0.16 hour. If I say only 10 minutes, so if I say only 10 minutes instead of 3, you have to substitute as 0.16. So 10 by 60. Okay, so 60 means 100 as far as time is concerned. So if I say 10 minutes means it is 0.16. Okay, so 3 hours means this is 3. So 100 plus or minus 20 by 500 into 3 into 100, that comes to be 100 minus 12, that is 88%. That means if I'm extracting 20 ampere from the battery source, 20 ampere from the battery source, which is a 500 ampere hour battery source, for almost 3 hours, we are going to find that there will be a drop of only 12%. Only 12% drop will be there, and after 3 hours, still 88% charge will be remaining inside the battery. Okay, so I will be changing the figures and all, and I can ask you this question, and you have to answer this in a numerical. So this is how the battery state of charge is calculated. If there is any doubt, you can raise question. This is discharge characteristic of a standard lead acid battery. You are finding that starting voltage is 2.05. That is the best. Generally, we call it 2. So this 10 means you are asking for 10 ampere discharge current, and it is almost going for 100 ampere hour. So you are saying that if it is 100 ampere hour is the capacity, you are finding the cell voltage. So for a 100 ampere hour capacity, you can get 10 ampere almost for 100. Okay, so this is 100 ampere hour for almost 100 hours. You are finding if you are asking for more ampere, you are finding that time is becoming less. If you are asking for 100 ampere from the battery, okay, so it is starting itself is from 1.85. One very interesting thing you can see here that the starting points are changing. If you are asking for huge amount of current from the battery, your battery cannot give you 2 volt. Your battery is starting from 1.85 volt. So this is where you are damaging the battery. A very important graph you have to understand. So this graph also I can ask you in the exam. That is, explain this graph. That means if you are asking for too much current from the battery, 100 ampere or so, the battery is not discharging from 2 volt. Though it was charged at 2 volt, though it was its initial voltage, but as you're asking for too much of current, it is giving best voltage as 1.85. You're asking for 70 ampere, which is little less. You're finding that you are going closer to 2 volt. Okay, you are asking very less current, 10 ampere. In that case, it is starting from 2.03. So 2.03, this you remember, whenever we are saying that it's a lead acid battery, you can write down it is 2.03 volt is the starting point of the battery. So 10 ampere means it can give you 2.03 volt. That is the starting point. So this graph is very important. It's a practical graph. You can find out that more current you are asking from the battery, it is actually starting from a lower voltage. So for EVs and HEVs, energy capacity is more important than ampere hour. In the colorimetric capacity, the energy capacity is directly associated with the vehicle operation. Energy delivered from the battery can be expressed as EV is equal to VI and SOC. Okay, VI and SOC. So this is the input voltage, and this is the SOC, how much is the charge remaining, multiplied by IT. So voltage and current multiplication is nothing but power. Okay, you are integrating the power, then you are getting energy. Okay, so this is the relationship between energy is equal to power is equal to energy by time. And if you are integrating power over time, you are getting energy. So this equation also you have to remember, that is voltage and current multiplied together, and that you are actually integrating over time. So voltage and current is nothing but power. You are integrating power over time is actually you are getting energy. And unit of energy is joules. Okay, V is the terminal voltage. V is equal to a function of current and state of charge. So this 2 slides or these 3 slides are very important. That is this one ampere hour characteristic, this one state of charge, and this one discharge characteristic of standard lead acid battery. So give time to understand this and understand everything. If you want a discussion, we can have another in the class. These slides I'm not going to ask in the exam, but there are some equations and all. You are talking about a PbSO4 type of, so Pb is nothing but lead. So this is electrochemical reactions in a lead acid battery. So this is an example here. So Pb anode electrically negative, PbO2 cathode electrically positive. During discharge, lead is consumed and lead sulfate is formed. So the anode chemical reaction is given, cathode chemical reaction is given. We are finding that here it is 2E minus, here it is 2E minus likewise. So there is one cathode, one anode. So who is going where? All these things are shown here. So this will not be there in the exam, but as they have asked construction of lead acid battery, we should at least see this. And I think few of you are very good in electrochemistry, so you'll be understanding all these things. So 2E minus. So 2E minus is, this is the thing we are interested in. Okay, so whenever I'm saying the free electrons are available in anode. Okay, that means free electrons are available in electrode. In that case, we are saying that those are the free electrons which are getting deposited in electrode that will be actually used for electricity conduction. So gist of electrochemical reaction in lead acid battery. So all these things are given. Finally, it is written that lead acid battery has a cell voltage of 2.03 volt. Very important thing I told you in this slide, in the previous slide, that 2.03 volt is the starting point. Here you are finding whenever it is 10 ampere, you are getting discharge. Here, this point is 2.03 volts. So this can be one question I can ask in short question, that is, how much can be the maximum voltage of a lead acid battery which is used in the vehicle. So such 2.03 volt, if you are stacking, how much will be the total voltage? So 2.03 volt lead acid battery is connected in series, means it will be 12.18 volt. That you have to understand. So that 12.18 volt battery is connected in normal passenger car, 12.18 volt. And if you're talking about a very big truck or something, they are actually using two such batteries. So it will be 24 volt, but actually it is 24.36. Okay, such 2.03 volt, such 12 things are connected in series. Okay, actually they are using two batteries of 12 volt each in very big vehicles. That is actually there are 12 batteries, though we are saying it is 2 battery, but each battery is having a stack of 6. Okay, so this is 2.03 is a very important thing. Each lead acid battery is having 2.03 volt in standard condition, which is affected by the concentration of electrolyte. So these are some of the small things. If you remember, it will help you in your interviews and to design the system. Okay, so this can be asked in the exam. What is meant by Gibbs free energy? So a little bit touch of thermodynamics I have given here. From this, but can be asked. So one definition is what is meant by Gibbs free energy, which is given by delta G. Another is what is meant by reversible voltage of the cell. So those who are having pen and paper, you can write down these two questions. What is meant by Gibbs free energy? What is meant by reversible voltage of the cell? All those things you have to understand. So thermodynamic voltage of the battery cell is closely associated with the energy released and the number of electrons transferred in the reaction. Energy released by a battery cell is given by the change in Gibbs free energy, which is given by delta G. Delta stands for change. Okay, so how much charge was initially in the battery, and after you are after you are driving the load is nothing but the motor. After that, after certain time, how much is going to be the remaining energy in the battery. Okay, so this is the difference between that. How much is the energy released given by Gibbs energy. So delta G is equal to Gi minus Gj. So Gi is nothing but products, they are reactants. So delta G, that is a Gibbs free energy, is given by minus NF V gamma. All this equation can be asked. N is the number of electrons transferred in the reaction. That means electrochemical reaction. F is nothing but the Faraday's number. It's a constant 96495. We have done this in 12th. And there is something else which is called as a V gamma is the reversible voltage. Or I think VR it is, not V gamma. I'm sorry. Because VR is the reversible voltage of the cell. In a standard condition, 25 degrees centigrade temperature, 1 atmosphere, VR0 is delta G0 divided by NF. Okay, so this is the reversible voltage, Gibbs free energy, number of electrons transferred, and Faraday's law of constant. So you're finding that delta G is directly proportional to N and VR. And why is it minus? Why there is a minus here? Because there's a energy released. So there's kind of a discharge. That's why it is minus. So there's a kind of energy loss. Okay, that's why this minus is coming. Likewise, in the previous slide, we had found that discharge current was shown in negative. Okay, so this is the formula you should remember. Delta G is equal to minus NFVR, where VR is it's called as a reversible voltage, and what is the definition is given here, and the standard temperature standard or ambient pressure standard is given here. So this VR is measured at 25-degree room temperature and 1 atmosphere outside pressure. Now I'm coming to the next slide. These are also explained thermodynamic voltage. We're starting from the same equation, and finally we are finding VR is equal to VR0 minus RT divided by NF, natural log of activities of products, activities of reactants. So inside the battery, there are two things. There are actually three things: cathode, anode, and electrolyte. Okay, and they're actually reacting with each other, and they're producing some products or byproducts. So what are the products activities? What are the reactant activities? They are actually put into a ratio. They are taking natural log of that, R into T divided by NF, negative of that, and you are actually subtracting it from VR0, where R is the universal gas constant, 8.31 J mole per K. So these are just for your knowledge. I'm not going to ask all these things in the exam, but yes, from the previous slide, it can be asked, that is, what is meant by Gibbs free energy, what is meant by this VR, reversible voltage. These two definitions can be asked from this slide only for 2-4 marks. This slide, no question will be asked from here, that is for sure. Okay, this is just for your knowledge. But yes, whenever you are going for interview like Daimler or maybe some battery related thing, they might ask you all these questions. So prepare it for your interviews. Last definition. This is the last slide for today, and then I will show you a video. This slide is very, 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 very important. Okay, it is defining actually specific energy. And whenever we are doing next lecture, we will start from the definition of specific power. What is meant by specific energy? Okay, and I told you that for electric vehicle, we need high specific energy source. So specific energy is directly proportional to how much distance it can cover, or what is the range it can cover. Specific power is actually related to its hill climbing or other acceleration and all those performances. So if I tell you that specific energy is like a batsman in T20 who is coming to open the innings, and it is playing for 20 overs. And whenever I'm saying it's a specific energy source, so it's like a batsman who is coming in the first over, playing for all 20 overs and scoring 80 runs. Specific power source, it is a high discharge source. So they are like the power hitters. They will be playing for 3 overs and they will be scoring for 40 runs. So this is the very difference between specific energy and specific power. So high specific energy means continuously over time, it will give you a steady high power or high energy throughout the driving operation. But whenever I'm saying specific power is high, means it will be used only for a very small time frame, and it will be giving you bumper energy. Bumper energy means it will play for 3 overs and it will generate 40 runs, or it will be run for 10 minutes and it will help you to climb the hill. And as soon as you go to the top of the hill, again you will come back to the specific energy source, right? So specific power source actually is acting with addition of specific energy source. So specific energy source has to act always. Specific power source is only during hill climbing or in bad road. It is actually addition to the specific energy source. So this is the last slide. We are going to see what is meant by specific energy. Specific energy is defined as the energy capacity per unit battery. Specific energy source is called as defined as the energy capacity per unit battery. Weight per kg, watt hour per kg. That is very important. Okay, so battery should be of lightweight and it should be giving you a very huge amount of energy. This is the source which is having high specific energy. So specific energy is defined as the energy capacity per unit battery weight. So if the battery weight is 5 kilos, and if the total energy given by that is 10 watt hour, that means it's having specific energy of 10 divided by 5, that is equal to 2 watt hour per kg. And in next lecture, we will see what are the components of a battery which are actually contributing to the high specific energy. You'll be finding that there are almost 60 to 70% of the battery components, they are not used for energy generation. Like the casing of the battery, it is not doing anything in the energy generation, but it has to be there. Okay, so we have to design battery with high specific energy. For that, we have to make the casing lighter but sturdy. Okay, so this concept you have to understand. We will explain in detail in the next class. So specific energy is defined as an energy capacity per unit battery weight. So lesser is the weight, higher is the energy, higher is the watt hour generated, it will be having high specific energy. The theoretical specific energy is the maximum energy that can be generated per unit total mass of the cell reactants. If you're not thinking about the battery sides, that is battery casing and electrode weight and all those things, you are only concerned about the reactance. In that case, a specific energy is actually calculated. So maximum energy that can be generated by per unit total mass of the reactants. So we have seen in the previous slides, that is PB, electrode, PbSO4, all these things are mainly reactants and electrolytes. But whenever you are calculating specific energy, you cannot say that I'm not going to consider its weight for casing and all those things. So whenever you're saying battery is a total thing. It's not only about the reactants or electrodes, it is about a total thing. Energy in a battery cell can be expressed by the Gibbs free energy delta G with respect to the theoretical specific energy. Only the effective weights. So effective weight means reactant weight. Total battery weight means there are certain things in the battery which does not take part into energy generation. But that also has to be considered when you are calculating the overall specific energy of the battery. E-spathio means specific energy theoretical. Okay, E-spathio means specific energy theoretical is equal to delta G, Gibbs free energy. Gibbs free energy we have seen minus NF and VR divided by 3.6 into MI is equal to NF VR divided by 3.6 and summation of MI. What is MI? MI is the sum of molecular weight of all the individual species inside the battery reaction. So all these things I can ask that how we are calculating the theoretical specific energy for any battery. So you have to write this formula NFVR 3.6 MI. All these parameters you have to explain. So F is a constant, VR is a voltage, and N is number of electrons which are used during discharge. So taking the lead acid battery as an example, VR is equal to 2.03. So I think now you have understood what is meant by VR. It is the maximum voltage where you can charge the battery. So 2.03. N is equal to 2, summation MI is equal to 642 gram. That means these are the reactants. This much is the reactants you have put in the battery, 642 gram. E-spathio is equal to 170 watt-hour per kg. You know the value of F, you know the value of N now. Okay, you know the value of MI, 642. Put all these things together and just calculate that E-spathio is 170 watt-hour per kg or not. This is found from the formula given above. What is meant by that? E-spathio 170 watt-hour per kg. That means whenever I'm talking about a lead acid battery which is producing 2.03 volt, for every kg of its weight, it is actually giving you 170 watt-hour. So higher the value is better. We definitely are sure higher the value of E-spathio is better. How can the higher the value be higher? The value will be higher if the VR is high, but VR we cannot change because VR is 2.03. If we cannot change, N we can change. So if it is discharging more, in that case, E-spathio will more. Okay. So whenever I'm saying it's a high specific energy source, for that, this 170 value should be as big as possible. So from specific energy equation, it is clear that the highly electromagnetic element, electronegative element and highly electropositive element, that is reactants, both of low atomic weight produces an ideal couple. That means all the reactants should be having lower atomic weight. So in that case, we can pack the battery with more amount of or more mass of the elements. So hydrogen, lithium, or sodium would be the best choice for the negative reactants. Lighter halogens, oxygen, and sulfur are the best choice for the positive reactants. To put such two couples, that means positive reactant, negative reactant, what goes best with what? But together in a battery requires electrode design for effective utilization of the contained active material as well as the electrolytes of highly conductive and compatibility with the material in both the electrodes. That means whenever I am saying it's a lead acid battery, at that time, what can be the positive reactant, what can be the negative reactant, all those things they have explained. So I am removing this slide now. So I'll just try to show you a video, and it's a very small video, not a very big one. Okay, I'm trying to launch it. Just give me some 2 to 3 minutes. I will show you that video. Though I can post that video, yes, I can post that video, but I'll show you that video and we will stop. It's a small video. I'll upload it, and it is a 5.35 minutes video, but I think I will make it short, right? So just let me, if you can listen to this, and entire screen I'm sharing. Okay, so there is a video. If the audio is audible, please let me know. If the audio is audible, I'm playing it. Just audio is audible. Anybody seems to let me know. Is the audio audible? Is the audio audible? Anybody can tell me?
No, sir.
Audible, yes or no?
No, sir.
Now is it audible? I have played the audio.
No, sir.
No, sir.
No. Audible? Audio?
No, sir.
Okay, no problem. The audio, let the video be playing at its own pace. The same equations, whatever I have written, this fellow has explained all these equations. I will upload this, and this slide is now visible at least. This video is now visible. Battery SOC and their estimation. At least, can you tell me whether this video, I have stopped it, but it is visible or not?
Yes, sir, it's visible.
Yeah, so the same equation I have told you, same equation I have shown to you, but only one problem is, can you see this VT? Can you see this VT here? Anybody says yes?
Yes, sir.
Yes, sir.
Okay, so this VT, it will not be VT, it will be a delta T. Okay. So Mr. Chauhan, who has prepared this slide, he is actually making this correction. So this is not VT, this will be delta T. Delta T is the time step. So the same video, the same equations I have copied and I have put it in my slides. Okay, so the same equation you can prepare from here, and this video you should see, because those whoever will be working, this numerical visible to you, exactly the same numerical I have taken. Anybody can please respond. Battery SOC and their estimation. Is this video, is this thing visible? The answer is 88%. Can anybody please confirm? Battery SOC and their estimation. Is this page visible? Anybody can just say yes.
Yes, sir.
Okay. So this thing you have to just see, and just see this 5 minutes video. He has explained everything in detail the way I have explained it. And the same thing, some battery configurations also they have shown this in the right side. 0.6 ohm is the load. Load is nothing but the motor. So the 0.6 ohm is nothing but the motor resistance. And here this VT has to be actually delta T. There is no VT here. That is the only correction. Okay. And this is how actually the state of charge calculated. So this was a 5 minutes video actually, which I will upload in your Google